I'm Damir, I'm the CEO of Massa Labs. We are working in close ties with quite a few people here, with Polygon, also with Starknet. We act as a dev shop, but we specialize in pretty advanced stuff. So yeah, let's tackle one of those. First of all, I'm going to talk about AirScript, which is a language we are working on currently with Polygon Maiden. And the goal is that we're going to create a language where you can easily express stark constraints, arithmetic constraints, in a way that's portable, that's compatible, and that can be audited. Let's look more into it. So first of all, let's have a quick reminder on how Starks work. Typically, zero-knowledge Stark virtual machines look like this. When you execute them, first you track at every step of execution all the internal states, all the internal variables. You take each one of their values as columns, and every step is a line in a matrix you create that's called the execution trace. You also have the public inputs, so the program you have fed to the virtual machine to be executed, the inputs of the virtual machine, the arguments, and the return values of the virtual machine. And together with that, you need something called the AIR constraints. These are basically mathematical constraints telling the prover how the different little cells in this matrix called the trace relate to each other. For example, in the next step of execution, this variable should be this1 plus this1 from the previous state. And with these three ingredients, the Stark prover, there's many types of Stark provers, but they will work together and it's going to generate a Stark proof. This proof is compact, it's small, it's logarithmic in size depending on the size of the execution trace. And the cool thing here is that then you can take this Stark proof and feed it to any kind of Stark verifier, so a smaller computer typically. And this smaller computer can just take the AR constraints of the virtual machine, the public inputs, and the Stark proof, and they can just say, verify this very efficiently, and tell you whether or not this Stark proof is a valid proof that there was at some point an execution trace with these AR constraints compliant and with these public inputs. So this allows you to have a compact proof and verify efficiently elsewhere. The problem we have is that currently in the ecosystem, there's a very strong fragmentation. Basically, every time you want to write these AR constraints, you need to write them basically in the language that you target in terms of prover. So these provers usually act as libraries, and you're going to have to write the constraints in the language of that library, basically, and target a library. So if the library is updated, you'll have to rewrite your constraints. If you write for one prover, you cannot use another prover. So there's a problem with fragmentation here. Each one of those provers and verifiers has their own language, basically. What we're proposing here is AirScript. It's a human-readable, human-auditable language to express arithmetic constraints, basically. And we are working currently on a compiler, the AirScript compiler, that's going to take these constraints, optimize them into an algebraic graph, basically just a graph of additions and multiplications. And from there, we have a code gen step that will generate this kind of codes for the target prover. You can have multiple target provers and verifiers. We'll see later how it works. But let's take, for example, Winterfell. You give it the AirScript code, and it's going to generate Winterfell constraints directly. So the day Winterfell update the library, you don't have to rewrite all the constraints. You don't have to re-audit them. You got them audited once, you just recompile them. So that's one thing. Now, here is what AirScript looks like. So for those who are familiar with Starks, here's what it looks like. So this is a little module called the Fibonacci. We define the internal states that we're tracking. We define how many inputs and outputs we have. We define the boundary constraints, so how these columns are linked in their first and last steps to these inputs and outputs. And integrity constraints that explain how we move from one row to the next in terms of the constraints on the rows of the trace. So here, for example, we enforce that in the next row, B must have the value that A plus B had in the previous row. So it's quite simple and quite convenient for developers to write in this format. We, of course, have made this way more expressive than this. There's conditional constraints. You can use match statements. You can have evaluator functions to group constraints that are reused. There's list comprehensions for those who like Python. All of this is available, so you can already play with this. This is available and working right now. And the last addition to this language that we have added just recently is buses. So this allows you to have modules, to write just modules, and have these modules communicate between them. For example, when you write a virtual machine, you'll have an arithmetic module, you'll have, I don't know, a conditional module, a hash computational module, and using these buses, you can very simply exchange data between these components of your virtual machine. And here is how it works in AirScript. You define the buses, you define their initial and last states. Here it just says that the bus at the beginning needs to be empty and at the end needs to be empty as well. And then you have these integrity constraints where you can say that, for example, whenever the variable S1 is 1, I'm going to push this pair to be inside the bus. And if I want to read something from the bus, I can use the rem keyword here. So this is highly practical to write modular systems. And here's a quick final thing on the future of AirScript. We have a very broad vision on what's going to happen with AirScript. First of all, in the future, we might have higher level languages translate to AirScript. Of course, that's one of the visions we have. So if you're interested into this, please contact us. Also, remember, the idea of AirScript is that it can be audited. And once it's audited, you can keep the same script, and then you can just reuse it across different provers, verifiers, and it's not a problem. You verify it once. And of course, speaking of verification, formal verification is also something we are interested in, because if you can formally prove that your constraints are what you expect they are, you just have to have this one constraint set for your virtual machine, and then you can reuse it across all of this. You don't have to rewrite it every time you want to support some new prover or verifier software. And finally, in terms of targets for compilation, for now we target Winterfell. And there's work ongoing, almost done actually, on running a verifier inside Maiden VM itself for Polygon Maiden. And the idea here is that we do recursive proving within Polygon Maiden. We are, of course, open to collaboration to add more provers and verifiers here. And one interesting thing as well is that technically we could output VHDL, so hardware descriptions. You could literally take your virtual machine and turn it with AirScript into an arithmetic circuit and hardwire it into an FPGA, for example. That could allow for accelerating star proofs. We're also very interested for collaborations on this side, so if you are into this, please contact us. And finally, of course, let's build stuff with AirScript. Let's build WASM VMs, let's build RISC-V virtual machines, EVMs, maybe some Stark-friendly AI models that can be mapped to AirScript. Some ZK rollups, some ZK identity verification primitives. All of this is open. Just go check it out. It's here. If you want to work with us on this, we are very open. We truly believe that this could become the future standard of expressing constraints for Starks. So yeah, thank you for your attention, and let's collaborate.